Hi. So I am afraid I have to begin this lecture with a bit of apology. My initial intent was to spend the rest of the semester just solving problems in our designated textbook. But as I try to move along with the problem sets, it occurs to me that the nature of the problems that Zhang will put together were not really interesting. So I really got bored of solving them, and they were highly technical, first of all. And I didn't see a lot of value in spending all the time and brain power working through the solutions. And I decided that maybe we should spend the remaining few weeks in a much more productive way. And after some soul searching, I decided to land on a different book. This is a book called Electricity and Magnetism by Purcell and Morin, a third edition in particular. And in case you do not know this already, this is one of the classics of the electricity and magnetism textbook literature. So Purcell is the guy who invented the first working NMR machine and shared the Nobel Prize with Edwin Bloch for that. So he is someone who knows pretty much everything about electronics. And back in probably the 80s or something, he wrote this classic book, a textbook in electricity as part of a series on all aspects of physics, uh, published under the name of Berkeley Series of Lectures or something. So there are a couple of different versions of that series. There's one book dealing with the mechanics, and there's a book on statistical mechanics, and there's this book on electricity and magnetism. But I would say that by far the most celebrated and the most remembered book out of that Berkeley series was this one by Purcell and Morin. And the only drawback, even back in the days when this book first came out, it was celebrated as a classic of its kind. But there's only one drawback with the original version, namely that they were using the unfamiliar CGS system of units rather than the MKS system of units. And luckily, by the time they got down to the third edition, they were able to fix the notational convention altogether to the MKS system. So now we do have at our disposal this book, which has all the familiar notations. Okay, so this book is really good in many respects, and but obviously I do not have time to cover all of the book, and so what I'm going to do in the next couple of weeks is to pick a couple of themes from the book that I find worthwhile and also not overlapping with our previous book by Zhang Mill. Zhang Mill had a lot of themes covered, but there were also some themes that he left out. And some of those themes that Zhang Mill left out are still rather valuable. So I'll try to cover those in a somewhat thematic fashion. So what I mean by thematic fashion is that in this lecture I will cover a certain topic, and in the next lecture I will cover some other topic. And so each lecture will be sort of independent from the other lectures, not like all the previous lectures in the past 11 weeks or so. And I would guess that for these turn of lectures, I would probably not require you to either hand in homeworks or to solve problems. So your only requirements will be to just listen to these lecture videos from start to finish and just enjoy the lecture and spend the rest of the time on research and other stuff. Hopefully that's what you have been looking forward to all semester long. And I hope you're not too much against my decision not to hand out homeworks or summary assignments. All right, so let's get started. So I'm gonna cover chapter materials in chapter 4 of Purcell's book on electric current because the previous 3 chapters cover things that we kind of already know. And so I'll skip them. So here we go. Let's brush up on our knowledge of the electrical conduction in a metal. I think previously I only assumed that there's only one charge carrier, but in real materials, it often happens that there are many charge carriers. But of course, that does not mean that there are charge carriers other than electrons in a piece of wire. You can only have conduction by electrons in a metallic system. But if you look deep down, then even in a metallic system, you have what's called the bands. And electrons can reside in many different bands. So you have electron from band 1, and electron from band 2, band 3, and so on. So you can kind of label them as if they were different kinds of electrons. But of course, all of them have the same electric charge, you would think, because they're all electrons. However, even that is not really the case. Because in a metallic, inside a metal, you have something called the electrons, and then you have something called the holes. And the holes are, although fundamentally they are the electrons, in all aspects of their behavior, they act as if they were positively charged particles, not negatively charged particles. So what that means is that it's much better to treat a hole as if this is a charge plus E carrier rather than a charge minus E carrier. Okay. So this is something, unless if you don't know already, perhaps your course in solid state physics will get you ingrained upon. And but if you don't already know this fact, then you can just take that as a matter of given fact and just move on. So don't worry about it too much if you don't know what the heck is meant by electrons and holes. But just try to keep in mind that there can be several different types of charge carriers, even though they are all fundamentally the same electrons. They can live in many different bands and act as if they are different kinds of electrons, although they share the same electric charge. Okay, so now we have this multi-species charge carrier system. then the total charge density must be the sum of the charge densities of each species. And this sum represents such aspects of the charge carrier. And each charge density vector is given as the product of its own charge density, n alpha, multiplied by its own carrier charge, q alpha. And q alpha can be either positive or negative E, depending on whether the charge carrier type is hole or electron. And then, of course, there is this velocity of the each carrier type. Now, this velocity, of course, is itself an average quantity, because within each carrier type, of course, you have zillions and zillions of charges all moving at quite different speeds and directions. So when you say you assign a certain average velocity or certain velocity to a given charge carrier type, what you really mean is, of course, this average over all the velocities of the individual charges. Okay. Okay. And then there is this familiar Ohm's Law, which I hopefully do not have to repeat. But here's an interesting example that is being discussed in Purcell's book, and I thought this is sufficiently interesting for me to make mention in this lecture. So here's a situation. Purcell is an experimental guy, so he worries a lot about many of the practical situations that happen in real life experimental situations. And of course, that's a really valuable exercise, because so much of electromagnetism as a discipline is about solving experimental problems. Okay, so here's the situation that he wants us to consider. So now we have a wire of same cross-section everywhere. However, one half of the wire has one conductivity value, sigma 1, and the other half has another conductivity, sigma 2, because these two halves consist of different materials, sigma 1 and sigma 2, due to having, for example, copper over here and gold over there or something like that. So now you have this junction which separates the two different metals or two different materials, and you have some current flowing through this entire wire. Okay, so according to the Ohm's law, and also according to the fact that you must have exactly the same current flowing in as flowing out, you arrive at these equations, right? So if you apply the Ohm's law on this side of the wire, then of course you will have this relation. And if you apply the Ohm's law on this side, then you will have this relation. But J1 and J2 must be the same because of the current conservation. Now, to then satisfy the current conservation, what you have to admit is that the electric fields on one side, namely E1, and the electric field on the other side, namely E2, they cannot be the same. They must differ. and they must differ abruptly as you cross the interface. Okay, and now this sudden change, sudden difference in the electric field strength must imply that there will be some accumulation of charge at the interface. So remember, normally inside a conductor, you cannot have any non-zero charge density, even in the situation where there is a current flow. Okay, and this is something that we have proven a couple of weeks back, but hopefully you remember there was a catch in that proof. And the catch was that the conductivity must remain uniform everywhere in space. But here we are dealing with a situation where the conductivity is not uniform in space because of this sudden change from one region to the other. Okay, so when that happens, then it's entirely possible to have some accumulation of charge somewhere, even inside the conductor. And this is a simple setup which reveals such a situation. All right, so let's go ahead and try to calculate just how much charge is being accumulated at the interfacial region. Okay, so here is a blow-up image of the interface. So this shaded circle represents the interfacial region with a cross-section area A. And you have some electric field coming in, and you have some electric field going out. And I made the arrows over here much bigger because I'm assuming that the conductivity in the region 1 is bigger than the conductivity in the region 2. So in order to make up for the smaller conductivity value, the electric field has to be bigger. Okay, but then you can apply the Gauss theorem, which will quickly render this relationship. The field strength difference multiplied by the cross-section area should be equal to the charge that are trapped inside that volume. But the our assumption is that the only place where the charges can remain trapped is this interfacial region. Okay, so now let's bring in these old equations we wrote down over here and use that to write the electric field in terms of the current density and write the current density in terms of the current, and so on. And then plug these expressions back into the electric fields E2 and electric field E1, which will then, after some cleaning up, give you this relation. Okay, so now that nicely gives you the information on exactly how much charge is being accumulated at the interface due to the difference in the conductivities on either side of the interface. And of course, that amount of charge grows as the current grows. Okay, and that's also very natural. Okay, so this is a kind of neat result that shows that if the wire is inhomogeneous, then to kind of compensate for that inhomogeneity, you must necessarily acquire some charge accumulation somewhere inside the wire. Okay, so I hope that, especially if you're an experimental guy, I hope that's the lesson, kind of lesson that you can carry around and hopefully use when something goes wrong with the equipment in your laboratory. I was just saying it. Okay, so now let's move to the main theme that I want to discuss in this lecture, which is about the resistor network. Okay, so resistor network is a problem of solving the net resistance when there are many resistors, and then some of these resistors are connected in series, and some of them are connected in parallel. And you have not just one, two, or couple, but many resistors that are coupled in all kinds of fashion. And the problem that you have to solve is to find out exactly what is the effective resistance that you get out of this entire complex network of resistances. But of course, one thing we know from very early on is that there are these two rules for adding resistances, right? So if there are two resistors connected in series, then the effective resistance is the sum of the individual resistances. And if they're connected in parallel, then the effective resistance inverse is the sum of the individual inverses. And if you have many resistors connected in various fashions, then you must apply these rules repeatedly until you end up with only one effective resistor whose effective resistance can be calculated by also repeatedly applying these rules. Okay, so this is the basic rule that we're all familiar with, and we had some experience solving for the effective resistance of resistor network consisting of maybe 3, 4, or 5 individual resistors. And in solving such a problem, we probably had to also apply these rules known as Kirchhoff's rules. And there are two sorts of rules due to Kirchhoff. One was the fact that if you add up all the currents coming into a given node, then the net current coming into the node must be zero. That's just a consequence of current conservation, rather charge conservation. And then the second rule of Kirchhoff is that if you go around any closed loop, then the net voltage change around the closed loop must be zero. That's essentially related to energy conservation. Okay, so since you know these things already, I won't dwell on these too much. So let's have some fun applying those two rules. Okay, so ultimately, what we want to know is exactly how much current is flowing through every resistor in my site. So here is an example of some fairly complex resistor network, and you have some current flowing through every resistor. I call them R1, RI1, I2, I3, since there are 3 different resistors. However, according to the current conservation, what happens here is that the current I1, which is coming into this node, gets split into two different currents, I3 and I2. So that means the I2 and I3 added together must equal I1. Okay, that's an example of Kirchhoff's first rule applied to the first rule on the current conservation. And then there is a second Kirchhoff's rule concerning the voltage conservation, really. So if you follow along this loop, let me represent the loop with a rectangle enclosed by that loop. Okay, so in this loop, the voltage conservation requires that this equation be satisfied. And then along this closed loop, you have another voltage conservation, like this. Okay, so here we have three unknowns, right? I1 and I2 and I3 are the three current values that we want to know about. And luckily, we also have three equations that tell us information about the currents. So with three equations for three unknowns, we can solve them. This is just a linear equation. And then learn everything about the current on each passing through each resistor. Okay, but then of course you can just do that. But then you realize that actually the nature of these first equation here is quite different from the nature of the other equations over here. Okay, right? I mean, obviously the first equation is coming from first rule of Kirchhoff, and the other two are coming from the second rule of Kirchhoff. But then it's not just that, but what really stands out is the fact that this equation only involves the current, right? There's no other information like what is the resistance and what is the voltage. Okay, this is just about the sum of current being equal to the sum of other current. So the only variables that show up here are the current. So that makes it much easier for us to solve these kind of current conservation problems first. In this case, for example, by solving that, we can express I3 as the difference of I1 and I2. Okay, and then once that has been solved, we can just replace this I3 over here with I1 minus I2. So thereby we eliminate this equation and only get to work with these two equations, right? So instead of working with three equations, we just end up working with two equations. And that sounds a little bit simpler. Okay. Actually, you can implement that idea right from the very beginning. And to do that, you just have to realize one thing. Every closed loop, for example, here, there are two independent loops. Here's one independent loop, and here's another independent loop. Every closed loop can be given a certain value for the loop current. So this loop has the loop current I1, and this loop over here has the loop current I2. Okay. And why is it possible for us to assign a loop current, unique loop current for every loop, every independent loop in the resistor network? Well, that's essentially because there is this first rule of Kirchhoff about the current conservation. So the fact that we're able to even define a loop current means that you always have to have the same amount of current flowing around the given loop. But that situation always guarantees that the current at the node will always be conserved. So by assigning a loop current, in fact, you will have solved the first Kirchhoff rule automatically. And therefore, all you have to do is to solve the second Kirchhoff rules. Okay? So then we can immediately write down just two equations, not worry about the first Kirchhoff rule anymore, and just focus on the second Kirchhoff rule. And the Kirchhoff rule applied to each loop says that that this equation should apply for this loop here. And here we have I1 minus I2 because when you look at this resistor, you have I1 current flowing in this way, but you have also I2 current flowing in the opposite way. So they contribute to the voltage drop with a different sign, which is why you have this minus sign over here. And also for this loop, you can easily write down the Kirchhoff rule in this form. Okay. Now, it should be rather easy for you to realize that this whole set of equations can be formulated as a linear algebra problem. Okay, so you have some sort of resistor matrix like this acting on the current vector. So you collect all the current variables into a column vector, act on it with the resistor matrix, and the result is a column vector of voltages. Okay. So now what you want to find out is the value of I1 and I2 in terms of E1 and E2. Well, all you have to do is to find out what the inverse matrix of that is, multiply that inverse matrix on the column vector of voltages. And that will solve the problem for you. Okay, so once you start working with the notion of the loop current, then it becomes kind of obvious that the solving the resistor network problem is just solving some linear equation, which is in turn equivalent to finding an inverse matrix of some resistor matrix. Okay, so this relation between solving the resistor network problem and solving for the inverse matrix of resistor matrix, that connection was probably not very emphasized in your prior education. But in fact, this is a pretty important connection to remember, especially if you're an electrical engineer and have to work with literally thousands and thousands of resistors connected in all kinds of crazy fashion. And the other nice feature of this realization that this resistor network problem is really a problem of linear algebra is that in linear algebra, we know there's this principle of superposition. All right, so what that means is that if one set of vectors is a solution and another set of vector is also a solution, then you can take arbitrary linear combination of those two vectors and still find the solution. Okay, and since this resistor network problem is the same as the linear algebra problem, perhaps that principle of superposition should apply to the resistor network problem as well. And that's exactly the case. So in my next lecture, I'm going to exploit that superposition principle and try to go a little bit deeper into that idea. Okay, thank you.